Hi everyone, welcome back to yet another Euphoria Academia YouTube video where we do past papers and we talk about the tips and tricks that have to do with each question. Today we're going to be doing the Physical Sciences Physics Paper 1, May-June 2023 paper. My name is Ole, so without further ado, let us get into it. Alright, for today we're going to be doing some kinematic problems as well as Newton's first and second law problems. So let us get into it. So we're first going to start off with some multiple choice questions, and yeah, let's just start with 1.1. It asks us which one of the following quantities is the tendency of an object to resist a change to its state of motion. Well, that's actually Newton's first law, and you should know your definitions, and if you know your definitions, then you will see that that is actually number A. All right, number 1.2 is a bit of a kinematic vertical free fall question, where we have a ball that is dropped from rest at a height above a concrete floor. Right, so we have our, maybe let me just draw it there. Right, and the ball will be dropped at some height h, right? And what happens? The ball strikes the floor and bounces vertically up and down on the same spot on the floor. Alright, so this ball is thrown from this height. Alright, it's thrown and then it bounces and then comes up, bounces, comes up, right, on the same spot. Apparently, the velocity time graph for the bouncing ball is shown with points P, Q, R, and S representing different times during the motion. We should ignore the effects of air resistance, which tells us that this is a free fall question. At which time does the ball reach its maximum height after the first upward bounce? All right, so we're just going to look at the graph here. So on this graph, we have a positive velocity, and then the velocity is decreasing, passes P, and then goes up. So essentially, this is actually, this part can be deemed as our sort of our first bounce, right? So it will, so this the velocity for the bouncing ball, right? So it essentially bounces from here. So at time 0 we have it going up, and then it will reach some maximum height, and then it will go down, and it will have a negative velocity of some magnitude when it hits the ground again. So that whole thing is our first bounce, and then it will go up again. Now, where we have our velocity equaling 0, that's essentially the maximum height after it has left the ground after the second bounce. Right? So after saying that, that's actually the answer. Q is the answer. So we'll see that B is the answer. For 1.3, we have a situation where we have two blocks P and Q of masses M1, M2 respectively, and they're held at rest on a frictionless horizontal floor with a compressed spring between them. Right? So when the blocks are released, the spring drops to the floor, block Q moves to the right. So this block Q will move to the right, and we're asked which one of the following represents the momentum of block P after the blocks are released. Well, this is essentially Newton's third law to a certain degree, because this spring was compressed because of this block P as well as this block Q. Now, when it is released, right, we will have a situation where block P actually is imposing a force onto Q, as well as Q imposing a force onto P. Right, now this will be in the form of the momentum. Right, so we know that this is going to move to the right, and by virtue of that explanation, that would also move to the left, maybe not as much, because we have lesser momentum pushing that way. But essentially, what the momentum for block P will have, it will have the momentum of M2 multiplied to some V, right? Because Q is actually pushing onto P, and then P is pushing onto Q. So our answer is going to be number D. Alright, the last question that we're going to do for multiple choice is 1.5. A hot air balloon is moving vertically downwards at a constant speed. Yeah, they even made a bold statement of it, which essentially means that our sum of forces will be equal to 0. They cancel out. Assume that the mass of the hot air balloon remains constant. Which one of the following physical quantities associated with the hot air balloon changes during the motion? All right, so the weight will not change, the force of gravity will not change, the momentum change, right, it won't actually physically change, right, even though well, actually it won't change, because momentum is just mv, and we're told that that is constant, right? And by virtue of v being constant, that means that that will also be constant. So the only thing that is changing is actually the height, right? And that we can see in mgh, that will change, so therefore D is the answer. Alright, now to the main part of this question or this video. We're going to be doing question 2, which is a Newton / kinematic problem. We'll see in just a few bits. And it starts from question 2.1, ends at question 2.5, and it is worth 17 marks. So let us get into it. I first like explaining what is going on in the problem, so that we know exactly what is what it is that we need to do with the questions that we're going to get. So we have a block A of a particular mass that we're not given, and that is connected to block B via a string that does not compress or does not extend, which means that everything is just translated to each other. So whatever acceleration that we're going to have in one is going to be translated to the other block, right? And it is passing over a frictionless pulley, which further reaffirms what I just said. And then block B is initially held at a height of 1.5 above the ground, while block A is initially stationary on the ground. All right, so these are probably going to be released, and when this is released, block A will also travel a certain amount, and I'm sure they're going to ask us for the height. But after understanding what exactly is going on, then I think you can attempt the question. All right, question 2.1, we are asked to show that the magnitude of the acceleration of block B was 3.88 meters per second squared, while the block was moving vertically downwards. All right. So we are also told that when block B is released, it moves vertically downwards and strikes the ground with a velocity of 3.41 meters per second. All right, so with that being said, we kind of have like a kinematic problem, because we're just meant to find the acceleration, right? And it's going to be a constant acceleration. We're meant to ignore the forces of air friction and stuff like that. So we can use our kinematic equations. So we're going to see that I'm just going to use Vf squared being equal to Vi squared plus 2a delta y. Right, now our Vf squared, we're told that that is 3.41 when it strikes the ground, and our Vi is actually 0 because we're told that this thing is held, so at a point, so that means it's stationary, and that will be plus our 2a because we're trying to find our acceleration, and our change in y will actually be the final one is 1.5 meters, and we can just do that as 0, right, just to make things simple for us. All right, now we're going to find that our a is in fact equal to 3.876 meters per second squared, which if we round off to 2 decimal places, that's 3.88 meters per second squared. For question 2.2, we're asked to draw a labeled free body diagram showing all the forces acting on block B immediately after it was released. Okay, so now it was released, so that means it's not held by something, so we don't have to account for that. So let us just draw the forces at that point. So this thing will be accelerating down, but it will be prohibited by the tension, which will be connected to our A through the pulley and that whole system, right? And it is going down. This is supposed to be vertically down, apologies, as a result of the weight. And that is our free body diagram. And it's even 2 marks, so that gave us an indication of what to expect. Alright, 2.4 asks us to calculate the value of m by applying Newton's second law to each block while they are in motion. The question actually just tells us exactly what to do, but let me just do a free body diagram for block A. I'm a visual learner, I'm a visual person, so it does help me. Alright, so we're going to have, so while this thing is moving, right, so it has left the ground at this point in time, but it will be pulled up by the same tension that we had in the free body diagram for block B, and it will have a restrictive force of the weight as well. All right, cool. So we're told to apply the Newton's second law to both of the blocks. So our F resultant, is equal to our MA, and from the free body diagram, well, we'll take up as positive because this thing is accelerating up, so that would make our tension positive and our weight negative. So that's going to be T minus W, where we're looking for M, A, and that's going to be T minus our M that we're trying to find, multiplied by our gravitational acceleration, which is equal to, now the acceleration that we found even if your guess was, or you showing the proof being wrong, just use the number in the question, which was 3.88, and that is multiplied to, oh no, sorry, that's not multiplied to a, just gave you the a, that is multiplied to our m. And after doing some algebra, we can see that our t is equal to 13.68 m. That's not meters, that's our variable m. Alright, now for block B, we have a situation still. We're going to use our resultant force being equal to MA, where we're going to take, where's this thing accelerating? It's accelerating downwards. So our downwards, we're going to take that as positive. And with that, we're just going to replace what we had from the free body diagram. Our weight minus our tension in the string is equal to MA. And what is our weight? Our weight is 7.5 multiplied to 9.8 minus the tension that we're trying to find. Our mass in this case is 7.5, and our acceleration is 3.88. Now, after some algebra, we're going to see that our tension is equal to 44.40 newtons. Always try and keep your things to 2 decimal places, as we have, well, all over. Right, now that we have our value for our t, we can just take that and then replace it with that, where we have 44.40. That will be equal to 13.68 m. Remember, that's a variable, not our unit for length, meters, right? So that is going to give us a value of m will be equal to 3.25 kilograms, and that is our mass for block A. Alright, so for the last question, we are told, or we're asked to calculate the maximum height above the ground reached by block A. Now, we need to understand exactly what is going on here, right? So this block B, it will accelerate downwards with that acceleration that we did calculate, right? And it's going to reach the ground, hit the ground, and stuff like that, right? But this block A will also, because there's a movement of 1.5, it'll also get to a point. Okay, let me just draw that to scale a bit. Alright, so it will get to a point where it is also, I know that's not really 1.5, but it will also go to the point of 1.5 because this has moved 1.5, but because there is an initial velocity, right, this block A will actually go past this 1.5 just slightly because of that initial velocity that will still be in the system as it accelerates up. Now, it will only be stopped by, well, when this block A moves, it will move, and then the thing that's prohibiting it would still be the weight, right? So essentially, there's going to be a height where this thing will stop that is slightly higher than that 1.5. Right? So let us go through the calculations. Alright, so we still have our kinematic equation of Vf squared is equal to Vi squared plus 2a delta y. Right, now our final velocity is going to be 0, it's going to be stopped, and that initial is also the same for our block A coming from block B, plus we're going to have 2 times. Now note, this acceleration is not, I'm not going to account for the acceleration of the system, but it's actually going to be due to gravity, right? Because it's trying to stop this thing from going up, right? And we're trying to find delta y. Well, we're going to find that our delta y is going to give us an amount of 0.59 meters, and like we said, that's not the maximum amount, but the max amount is going to be the 1.5 meters plus the 0.59 meters. So that acceleration of 3.88, we actually, it was accounted for here, where we, because that's the acceleration of the system, and this height change is the height change of the system only. Alright, so our maximum height is going to be 2.09 meters. And just like that, that is our questions.